Disk wins. So take it away, Joey, and remember to call out when you need to change the slides.
Yeah, well, thank you. Well, normally I would say it's great to be here, but I guess I have to say that it's great to be a disembodied voice. I'm happy to talk about STROBE-X and the physics of disk wins. If you can go to slide 2, please. So, over the last 20 years, I trust this doesn't need all that much introduction, but with radio and X-ray and optical and infrared studies of stellar mass black holes and outbursts, we've developed a picture of basically how feedback works, connections between accretion and ejection processes around black holes, with stellar mass black holes periodically every few years to every few decades, going into outbursts and rising and falling in luminosity with correlated spectral changes that are associated with major physical changes in the accretion disk and the corona, moving from hard states that are dominated by pocket scattering in the corona to softer states that are dominated by disks, and the hard states dominated by jet emission and relatively little steady jet activity during these softer states. So you've all seen these talks before. I'm sure there are already been talks about it. But this is the way that we've come to understand sort of the feedback, mechanical and radiative feedback processes in X-ray binaries. But when you look with Chandra, if you go to slide 3, please. If you look at high spectral resolution with Chandra, at some portions of these outbursts you see strong absorption lines. And there's a lot of astrophysics, there's a lot of good atomic physics, and there's a lot of good astrophysics in those lines. They contain information about the density and the temperature and the ionization of gas. They tell you about how much of this absorbent gas there's along the line of sight, about how fast it's moving, where it's located, and where it comes from. So if you're interested in understanding accretion and ejection processes around black holes, studying winds and how they vary over time as they do in these two spectra of the black hole GRO G1655-40 from 2005, understanding how these winds vary over time is really important. If you go to slide 4, please. So it's important to try to put our understanding of accretion disk winds from spectroscopy into context of the black hole outburst diagrams that we know and love. Gabriele Mondi and a few of us did this work in 2012, looking at our Untitled study of all the available X-ray observations that were capable of probing accretion disk winds and putting those detections onto the hardness intensity diagram. So you have this normal hardness intensity diagram. We see the same Q pattern that we know and love. And the circles represent detections of accretion disk winds, and the triangles represent non-detections. So what we see is that disk winds are preferentially detected in softer and brighter states, as opposed to the harder states that are dominated by jet activity and the corona and compass scattering. So it's evident from work that Buren Hellman did last year. We had a paper that indicates pretty clearly that there's not, at least as far as we can see, there's not necessarily a clean line between states. It's not, there's not a strict dichotomy of absolutely no winds ever in hard states and absolutely never jets in soft states kind of things. But so there's some complexity there, but there's clearly a trend. If you go to slide 5, please. There's two reasons that this trend is particularly interesting, that this state dependence of winds is important. And the first is that winds can be extremely massive. If you try and estimate the mass loss rate in these variable ionized winds, what you can find is that in a number of cases, they can be significantly greater than the accretion rate at the event horizon. And when I say significantly greater, I mean factors of 10, 20 larger than the accretion rate, so that we have some external mass supply, that's being supplied to the disk from a companion star, and say 95% of that material is actually being ejected by the wind, and the 5% that trickles down to the event horizon is what's responsible for the luminosity that we see. So in that context, accretion disk winds are actually responsible for regulating the accretion rate at the event horizon. And this is an interesting interaction because of the way that winds can be produced by the radiation field to begin with. So there's a lot of fun astrophysics in understanding that, but they're clearly playing an important role in the way that the accretion rate evolves during black hole outbursts. Slide 6, please. The other important point about this trend is that accretion disk winds are extremely variable, and they can vary on timescales as short as a few seconds. I'll show you some examples of this, up to years. And so, especially for STROBE-X, the fact that these are such variable phenomena is a really great way to study the physics that connects black holes to their environments, to understand how the variability that we see in radiation translates to variability in the environments of black holes. So just to show you a few of the fun things that we might be able to see with STROBE-X. Slide 7, please. Example that's now relatively old from GR's 1915, so 105, where you have a large-scale, a bright pulsation that lasts about 50 seconds. In the X-ray, we call this heartbeat state. Jack Steiner is doing some nice work of nicer on similar variability that we've seen already there. But so you have this bright X-ray pulsation, and at the same time, when you looked at this pulsation with Chandra, what you see is evidence of the accretion disk wind. And if you track how the wind varies with the phase of that pulsation, what I found in 2011 is that there's actually evidence that the bulk of the wind is responding on very, very short timescales of seconds. So in the bottom right here, you see this phase-folded pulsation at the bottom panel with RXTEs, that sort of double-peaked light curve profile. And then above that, you see the absorbed flux in the iron line as measured by Chandra. And you can see that they have that same sort of characteristic pulse. So that I think is really neat, and you're seeing that change in just a few seconds. And if we think that the winds are something like 10 to the 11 centimeters from the black hole, which I'll get to in just a second, the fact that they're able to change on such short timescales is actually physically really interesting. Slide 8, please. Another example, I'm sure many of you know that exotic examples from GR's 1915 abound. Here is a sort of hour-long cycle called the main state in GR's 1915 that's associated with alternating periods of intense bright variability and then fainter dips. And if you just slice up the observation into the natural sort of bright and faint intervals, you see significant changes in the absorption lines from the accretion disk wind as illustrated on the right. So those are some sort of crazy light curves that we might see just looking at GR's 1915 and evidence that we should expect to see changes in the accretion disk winds on those same kind of timescales. But these sort of results, these studies that we can do of variability with winds are not limited to 1915. If you go to slide 9, please. John Miller had a paper in 2006 with Chandra looking at H1743 minus 322 during its outburst at the time. And he found that there was relatively low amplitude, I don't remember the RMS, but a small oscillation with a rough period of about 300 seconds in the light curve. And when he chopped that observation by flux, looking at the higher and lower flux periods of that oscillation, he found evidence of changing absorption in the iron line. So here what you're seeing is the iron 26 absorption line at 1.77 keV, or 1.77 angstroms at 7 keV, and then on the right, the one that looks more variable is the iron 25 one at 6.7 keV. So clearly, even small-scale variations are detectable with Chandra. It's not always clear what the mechanism for these is, whether there's clumps in the wind, or if you're seeing periodic obscuration of the radiation field by some physical structure in the disk that's partly responsible for the variations, the luminosity variations itself. But in any case, there's clearly a lot of opportunity opportunities for studying variability of winds with STROBE-X. And then just to make the point even clearer, in slide 10, both NuStar and now NICER are doing great things with winds. For example, actually looking at a paper in 2014, looking at a wind in 40, 16, 30, minus 47, you can see here with lines, your iron line, and the residuals there on the right plot. And then Tackett showed this on the bottom panel in his talk at the head meeting, a nice observation of draft 1915 shows very, very nice, strong, high significance iron absorption lines for wind. So these sort of features are clearly in the wheelhouse for STROBE-X. This is something that, we have strong variability and we have strong features that we can detect very nicely. So slide 11, I did some simulations to try and show exactly what STROBE-X should be able to see. I'm looking at an exposure time about a kilosecond. I'm looking at the 210 keV X-ray flux of 4 times 10 to the minus 9, so it's about a sixth of a crab. I'm looking at a relatively strong wind, a total, like an equivalent wind column density of 10 to the 23. This is more or less typical for a strong wind that we would see from a stellar-mass black hole. It's relatively highly ionized with an ionization parameter of 10 to the 4. So I'm just showing in these two panels here a zoom in of the lower energy spectrum and the high energy portion of the spectrum. And the low energy panel on the top right, you can see a lot of really nice features in XOCA. 1 to 2 to 3 keV absorption lines that pop out really nicely. Because they're clearly not resolved in the same way that the lines are in the chopper spectrums that I showed before, but there's a lot of significance in those features. On the bottom panel, the bottom figure is the typical iron absorption lines that we have come to know and love. And you can see that that in the LAD in particular, these lines are extremely strong, very, very high significance. So if you look at just this observation, comparing a fit with no lines versus a fit with what I used is the ZXI DCF model to simulate an ionized absorber. If you compare a fit without that component in there versus a fit within that component, basically for the addition of 3 free parameters, you get a change in chi-squared of about, sorry, that shouldn't be reduced chi-squared, but you get a change of about 4,100. So this is an extremely significant detection of this wind. We have very precise measurements of the column density and ionization parameter in the wind, and even we're looking at several tens of kilometers per second velocity resolution. So that's competitive with the chopper gratings, and in fact better currently unless you have a very, very bright source. So that's really great. Can we go to slide 12, please? So you're looking at very significant detections of winds. For the same physical parameters, you could probably get a 3 sigma detection in about 50 seconds. So, actually I would like to have total exposure times larger than 50 seconds, but the fact that you can detect these significantly on such short time scales means you can do really great spectral variability studies of distance and outbursts. As I think I've tried to explain, there's going to be a lot of variability to see. Now, the fun thing about going to very rapid variability is they're not particularly sensitive to systematic errors. We were talking about this on the telecom the other day. Whether the response is perfectly known or not, at these shorter exposure times, the boson errors, your boson noise is going to be more significant than systematic errors anyway. So including a 0.5% or 1% systematic error is not going to significantly affect your ability to study this rapid variability. Slide 13, please. So then the questions for STROBE-X about winds are how do winds form, when they form, where they form, and how those processes relate to horizon scale physics. And you can learn a lot about the outburst evolution, as I said, and how winds connect to jets by trying to answer these questions. So to answer those questions, I'm trying to understand the density of the gas, how dense are these winds, trying to winds that are radiation pressure, thermal pressure, Compton heating, and magnetic processes. You can draw in ionization and radius space in terms of distance from the ionizing source. You can kind of do a process of elimination and draw regions of perimeter space where you expect to see these different outflows, or you expect to be able to confidently identify them. So, for the definition of the ionization parameter up there on the right, you can see that if you can measure the ionization, you can measure the luminosity. If you can measure the density, then you can place your wind on in this plot to figure out the mechanism that produces it, and then you can do all sorts of interesting studies to sort of extract the astrophysics and what it means for outburst evolution. Slide 15, please. And the key is that the ionization state doesn't respond instantly to changes in the radiation field. The ionization itself is basically instantaneous, but recombination is a little bit slower, and this introduces a lag between variations in the luminosity and variations in the ionization. The recombination timescale for a density of 10 to the 11 particles per cubic centimeter is 1 second. So this is kind of perfect for STROBE-X. Since that's about the densities that start to get interesting for winds. If you go to 16, so what we're looking at is we have variability in the X-ray from a source. That variability is passing through a wind. It's being then detected by STROBE-X, and if we can measure how long it takes for that wind to respond to variability in terms of its ionization, we can. The idea is we can tease out the density from that, and then again the density gives us the location of the wind and the launch mechanism, and that allows us to physically interpret the outburst wind evolution, to measure them, to calculate the mass loss rate in the wind, and determine the actual influence of this outflow on the accretion disk. So go to slide 17, please. So I think it should be clear that the LAD and the XRCA are really going to be excellent for studying rapid variability of the winds, and sort of the bullet point is that the response to the radiation field is where all this really interesting astrophysics is, and that is STROBE-X is perfect for that. And so the ability to monitor these systems with the Wi-Fi monitor as they go through their entire outburst evolution, they need really precise constraints on their state and spectral evolution. That's going to allow us to connect what we're seeing physically with winds to the diagnostics of the accretion state and all of the event horizon scale stuff that Javier and Jen Steiner are working on. It's going to be really interesting. So, and that will also allow us simply to understand whether we have something like a wind line. There was this idea of a jet line where jets would turn on and off when the system crossed this line. Whether we can actually understand the sort of the moment of formation of winds, or if they are more of a continuous process through outburst. If you go to slide 18, please. So there's a few things that you need to be able to do to do this science. First is measure spectral variability. Obviously, that is you can check that box off. The other thing you have to be able to do is measure the ionization parameter rapidly. I think that means you need spectral resolution for the LAD better than 300 eV. That's about the separation between R25 and R26. So if you can't resolve those, you're going to have a particularly hard time, since they tend to be the strongest lines in our spectra. You're going to have a hard time determining the ionization parameter. Ideally, you would be able to measure the ionization parameter once per recombination time. In real time, that's really only going to be feasible if the density is low. For the highest estimates of density in winds that we see, that would be in sub-milliseconds. So that's not quite feasible yet. But by stacking multiple cycles of variability, or using the sort of maybe the QPO reconstruction techniques that Adam Ingram has been doing really great things with, I think we'll be able to start probing variability on those very short time scales. So if you look like 19, just as a kind of an estimate, if you suppose that the luminosity increases by 10%, that should, in principle, increase your ionization parameter by, or your log ionization parameter by about 0.04. So for me, the question is, how how long does it take to achieve that precision on the ionization parameter? How long does it take you to get to a precision on the ionization parameter where you could see the response to a 10% variation in luminosity? And again, using the same parameters that I was showing you before, it looks like that's going to take about 1 to 200 seconds. So I'm showing 3 different sets of simulations, one with XRCA and LAD, one with in red, one with 0.5% systematic error added in black, and the one in blue with the descoped LAD effective area. And so you can see that the first 2 are not all that different. At very short exposure times, you basically get down to the precision that you need pretty rapidly. If you reduce the LAD area significantly, then you lose all that significance that we saw in those lines earlier, and that makes it a lot harder to study them quickly. So go to slide 20, and I'll start to wrap up. So basically what you want to do is accumulate enough exposure to study the recombination timescale and stacked data for interstate densities, something like 10 to the 12 per cubic centimeter. So I think you'll be able to do this with STROBE-X in a few tenths of kiloseconds, which, I'm not sure exactly what the sort of observation planning looks like, but I think that's great. I think that's a good target to hit. It's not, it's pretty wide. And then slide 21. I want to make the point that this is really a revolutionary diagnostic of accretion disk winds. This is something that we really can't do right now. It's the questions that Athena and Lynx are also pursuing similarly with microcalorimeters and gratings and very high spectral resolution instruments. So STROBE-X is coming at this with a different perspective, large area and timing capabilities. But it's clearly one of the questions that the next generation astrophysics missions, astrophysics missions, are really looking to and are going to be able to answer. And in sort of parallel with Athena and Lynx, I think we'll be able to then connect studies of outbursts of stellar mass black holes to AGN accretion, which is going to be really cool as well. So slide 22, please. I was a little bit surprised to see that despite the better resolution of the XRCA, that the LAD is going to be the main driver of studies of disk winds. Obviously, the descoped versions are less sensitive. That makes detailed rapid spectral variability a little bit more difficult. I think ultimately, if you reduce the effective area, it's just going to require longer integration times, but in order to get those stack variability at really short time scales, I think it's just hard to do it with the descoped. It's harder to do with the descoped missions. I think it's better to maximize the LAD to XRCA area ratio, and I think that cutting the LAD resolution